So now we're going to be moving forward into section 2.5. This section is really going to be trying to narrow down and tighten the screws on some of the specifics that we've been talking about in the previous videos. Now, we've been discussing the concept of a limit, this idea that we're moving on a function and trying to see where a function or the path of a function is leading us as x moves towards a particular value. However, the original definition that we gave back in section 2.2 regarding this topic was a bit vague. It included phrases like, we're going to move x close to 1, and we're going to make the values or the y values of the function arbitrarily close to L in order to have a limit. And it's really this idea here of close. What the heck does close actually mean? So we're going to try to add some rigor and exactitude to these sorts of statements in this section. Now this is probably, as a heads up, one of the more difficult sections in all of Calculus 1. And so don't be surprised if you feel very confused throughout the videos in this section. That's par for the course. It is the hardest topic. So the key is to really try to jump into it and understand the ideas. The biggest temptation here will be to just try to memorize a pattern of what numbers go where. But I'm going to try to encourage you to think about the general idea. All right, so let's think about what we have here. Let's suppose that someone came to us and said that they thought that the limit of the function 2x minus 1 as x approached 3 was the number 5. Now, based on everything that we've learned about limit laws in the previous sections, this seems like a totally reasonable conclusion because we have a polynomial here, we know that direct substitution applies, and we could do 2 times 3 is 6, 6 minus 1 is 5. That's great. But the problem with that is, how do we know that the limit laws that we were using in the previous sections were actually truthful statements? You might recall that back at the start of 2.3, I asked you to go out on a limb and believe me that those particular limit laws were actually true. And now it's the time to ask the question, how do we know that they're true? If they're true, then certainly this being 5 would make sense. But how do we know that those are true? And how would we prove this if we didn't have the limit laws? So here's at least the general idea of what we're hoping to do. What we want to do is we want to show that we can make the y values of the function f of x equals 2x minus 1, that we can make those y values as close to 5 as we would like, as long as we continue to select x values that are closer and closer to 3. Okay, the following picture is going to help try to illustrate this particular point. All right, so again, if we're working with the function 2x minus 1, let's suppose it has a picture that looks like this. And right here at 3, we know that up on the graph, there would actually be, right where this kind of hole is, if I was to fill that in, this would be the important point on the picture that we're moving towards, or that the path is leading us towards. At least that's what seems to be the case. But our goal is that if we wanted to prove this to someone, we would have to convince them that they could continually move along this path and continually get to y values that are closer and closer and closer to 5. They could get as close to 5 in a y value as they want. And the way that they would get closer is by continually picking values of x that are closer to 3. Notice, if I pick values of x that are really close to 3, then I'm going to get values of y that are really close to 5. That's how the function works. So what we're going to have to do here is start to talk about how far apart are certain x values from 3, And how far apart are certain y values from 5? And to do this, we're going to actually use two Greek letters, delta and epsilon. Now I'm going to kind of color code these right here. I'm going to use delta as a red value and epsilon here as a blue value. So delta is going to actually measure the distance from 3. So that is, it's measuring in x direction distance. So you can see over here, I have like 3 plus delta would land me at some other value down here on the x-axis. So delta in my picture is actually like this gap that exists right here on either side of that little dot. Now epsilon is almost going to measure the same sort of thing, but just on a different axis. It's going to be measuring the distance from the limit value of 5. So epsilon is going to be measuring the distance from 5 down to some other y value, kind of like these blue segments here on the y-axis. So I can see that there are y values that are different distances away from 5. 6 is 1 unit away. 4 is 1 unit away, and that distance of 1 would be represented by an epsilon. All right, so with all of this put together, we can notice the following. So I can say that notice when an x value is in the interval of 3 minus delta to 3 plus delta. If I picked an x inside of this space, any x at all, then the resulting y value that goes with that x will be in the interval of 5 minus epsilon to 5 plus epsilon. So this right here are some of the foundational ideas before we get to the definition. If I pick an x now that occurs inside of this delta interval, I get a y value back that will be inside of this blue epsilon interval. So let's go ahead then and see how we can actually use this to write out a definition down below. So here's our definition of how we're going to determine if we have a limit for a function. So suppose I have a function that's defined on some interval that contains the number a, like here 3, if that's what I'm moving towards. Then we'll say that the limit of f of x as x approaches a is some number L. Maybe we'll say it's 5. And we'll write it like this, as long as the following holds. We need to have that for every epsilon value that could be greater than 0. That is, for every gap in y values, no matter how big I want to make this interval, I could make epsilon a 10 and go from, what would that be? 5 minus 10 would be negative 5 up to 15. I could make a really big interval in blue. I could make a really small interval in blue, no matter what I plug in for epsilon. Every single time I pick an epsilon, for every epsilon, there is a number delta. Every time I set up a blue interval or someone gives me a blue interval, I need to be able to find a delta to make a red interval such that if x is in the interval a minus delta to a plus delta, then f of x, the matching y value, will be in the interval of L, that is kind of like our 5, whatever the limit value is, minus epsilon to L plus epsilon. Okay, that's terribly confusing. Let's try to break it down one more time. Again, what we're saying is every time that someone goes ahead and creates a blue interval, and they create that by picking epsilon. So every time someone picks a blue interval, we have to be able to identify a red interval, so that whenever we pick an x value in the red, the matching y values will be inside that blue interval. Now, if you try to think about why would this be the definition, think about the concept of a limit. If you're going to tell me that the y values of this graph keep getting closer to 5, then they should be able to get as close to 5 as I could ever want. If I want to create an interval that's this big, around 5, you have to tell me, Kyle, yes, you can definitely get y values that close to 5, just scoot a little closer to 3. And if I was even more skeptical, I said, well, I don't know, like, can you get inside of this interval? You could say, yes, Kyle, of course we can, but I'm going to have to give you an even smaller interval of x values. And as long as you can show me that no matter what sized blue interval I pick, I can always get x's to get that close, then I'll believe you that I can get as close to this value of 5 as I want. Now, this is a rather, again, confusing definition, and it does take some time to get used to, but we'll try to rewrite it and simplify it and do a bunch of different examples in the videos to come.